Hello everyone. In this video, I will provide an overview of the textbook section on independence and conditioning. Our brief outline for the video is we'll start off with joint probability mass functions, abbreviated PMFs, joint cumulative distribution functions, CDFs, marginal PMFs, independence, and then we'll look at conditional probability mass functions. And I should note that as we go through these definitions, we're doing this just for the case with discrete random variables only. We'll revisit these concepts when we talk about continuous random variables. So if x and y are both discrete random variables, we define the joint PMF as follows. P of xy is simply the probability that the random variable x is equal to a specific value x and y is equal to a specific value y. So we could express this type of joint probability function in a couple of different ways. We can actually try to write this as a function of two variables, or we could express this information in terms of a table with rows and columns. Let's take a look at an example where we use functions. So suppose that 3 balls are randomly selected from a box containing 3 red, 5 white, 3 red, 4 white, and 5 blue balls. Okay. If we let x and y denote respectively the number of red and white balls chosen, then we can express the joint PMF by the following function. Probability of xy is 3 choose x, 4 choose y, and then we have 5 choose 3 minus x minus y. Okay. Notice we're only choosing 3, so the sum of x and y is at most 3. Okay. And then in the denominator, we have 12 choose 3, because there's 12 balls in total, and this is the number of ways to choose 3 out of the 12. So if I have specific values for x and y, for example 1 and 2, we could calculate the probability. P of 1, 2 is equal to 3 choose 1, that's 3, 4 choose 2, that's 6, 5 choose 0, that's 1, so 3 times 6, 18, and 12 choose 3 is 220. And you can see now the function does, all the work for us in terms of getting the probability. We get 18 over 220. Our definition for the joint CDF, right? Remember, that's the cumulative distribution function, is that the joint CDF of a pair of discrete random variables is defined to be, we use the notation capital F again, capital F of xy. It's the probability of random variable x less than or equal to a value x, and the random variable y less than or equal to a value y. So knowing the joint CDF, we have a lot of information. One example is we could work backwards, okay, to get things like the CDF of just x alone. Okay, so we could do that by sort of letting y vary. Okay, and we could also work backwards in various ways to get a joint PMF. So here's an example. Suppose a company that services air conditioners would like to schedule technicians more efficiently. They've determined their PDF where x is the service time in hours of the location, right? So you can see here's x, and we assume x can take on the values 1, 2, 3, 4. And y is the number of air conditioner units at the location. So you can see y could take on the values 1, 2, and 3. And here's our joint PMF. Okay, so one thing we could check is that this is a probability distribution function, meaning that all these probabilities have to add up to 1, and they all must be between 0 and 1. Okay, so here is our PMF. Now from this, we want to get the joint CDF. So there might be various ways to do this, but what we're going to do here is sort of calculate these cell by cell. So I'll show you some of the calculations here for the first 2 rows. Okay, let's start by going along the first row. So the cumulative distribution of 1, 1 is just the same value that you get from the PMF. The cumulative distribution of 1, 2. So this is the sum of values where x is less than or equal to 1 and y is less than or equal to 2. So really this is just going to be the sum of these 2 values. Since x is less than or equal to 1, we have to stay in the first row. So we get 0.12 plus 0.08, 0.20. Okay. The cumulative distribution F13. Again, we must stay in the first row, so I get the sum of the first 3 items. And the cumulative for 1, 4, now I'm looking at the sum of all the items in the first row, we get 0.32. Now, suppose we wanted the values for the second row. Okay. So if I look at the cumulative distribution F21. Okay. So now we notice that we have to stay in the first column. So this value over here is the sum of these 2. That's how we get 0.20. All right, things get more interesting when we look at F of 2, 2. So now my x has to be either 1 or 2. My y has to be either 1 or 2. So we're adding up the 0.12 plus this 0.08, the 0.08 in the second row, and now the 0.15 in the second row, second column, we get 0.43. If I wanted f of 2, 3, okay, so now my x has to be less than or equal to 2, the y has to be less than or equal to 3, so now I have to add the values sort of in this 2 by 3 rectangle. 2 rows, 3 columns. When I add all of these up, you could see this adds up to 0.71. And this is how we would proceed. You should stop the video, okay, and try to get f of 2, 4. Okay, see if you get this number, 0.89. I would also practice with some of the values f of 3, 1, for example, 3, 2, 3, 3, and 3, 4. These are the values that you should get. Some other important ideas related to joint distributions are what is called the marginal PMFs and the independence of our 2 random variables. So let's start with the marginal PMFs. Suppose you're given a joint mass function for x and y. The mass function of x alone can be calculated by summing the joint mass over all possible values of y for a given x. This is called the marginal PMF for x and is denoted by p sub x of x, right? And of course, in a symmetric way, we can also find the marginal PMF for y, denoted p sub y of y, by summing over all values of x for a given y. Okay, so we'll take a look at this in a minute. I have an example. This is very easy to describe when your joint mass function is given in terms of a matrix. In this case, the marginals end up being the row sums and the column sums. All right, another related concept here is, let's suppose we have a joint PMF for x and y. Then we could define x and y as being independent if the joint PMF can be factored into the marginal PMFs, just like this. Okay. So what one has to do if you're given the joint PMF is not only factor it, but make sure when you factor it, the two factors are indeed the marginal PMFs. And this type of equation must hold for all pairs x and y. So if you're proving two random variables are independent, you have to show that this factors, and these are in fact the PMFs for x alone and y alone. So if you have a matrix, you may have to check for all pairs. On the other hand, if you're showing that two random variables are not independent, then you only need to find one pair of values, x and y, for which this equation is false. So here's another example. We go back to the PMF from the previous problem. Suppose we want to find the marginal PMFs and determine if x and y are independent. Okay, so to find the marginals, let's say we wanted to find the marginal PMF with respect to x. So x can take on the values 1, 2, 3, and 4. So what we need to do here is, for a given x, sum over all the y values, which in this case becomes finding column sums. So when I add these three numbers, I get 0.21. When we add over here, we get 0.24. Adding the third column, you can see we get 0.30, and the fourth column gives us 0.25. So here I have a new probability distribution function, right? One quick check is that these numbers should all add up to 1, right? And of course, you should not have any negatives, and the numbers should be less than 1. To find the marginal PDF with respect to y, we see that y can take on the values 1, 2, and 3. So now we need to find the row sums. For a given y, we sum over all probability values for all x. So summing up here, we get points. Let's see. You can see we get 0.32 when y is 1. We get 0.57 when y is 2, and 0.11 when y is 3. Okay, so these are what most people call the marginal PMFs. All right, so that's the solution for part A. Now in part B, we were asked to determine if x and y are independent or not. Okay, so this one is fairly easy to settle, right? What I'm going to do is I'm going to think of the value here in this cell, 0.12. So if x and y were independent, then if I take the marginal evaluated, well, the marginal with respect to x evaluated at 1.21, this row sum. No, it would be this column sum, the 0.21, times the marginal with respect to y evaluated at 1. That'd be this row sum, 0.32. If x and y were independent, when I multiply those two values, I should get 0.12. Okay. But what happens here is when I multiply those two values, we get 0.0672, which is not equal to the 0.12. So we could conclude that x and y are not independent. Okay, now the last important piece of this section is the idea of a conditional probability mass function. Okay, so the conditional PMF of a discrete random variable x given the value of another discrete random variable y is given by, well, here's our notation. So you want to think of this as the conditional PMF function of x given y. So we could express this as a conditional probability. Probability random variable x is a value x given y is equal to y. Okay. We could think in terms of this fraction. Might remind you a little bit of the definition of conditional probability. So here, I want you to think of this as the probability x is equal to x and y is equal to y. Okay? The probability our random variable x is equal to the value x and the random variable y is equal to y, divided by the probability y is equal to this specific value. I like to remember this fact here in this form. This conditional PMF function is equal to the joint probability function divided by the marginal, right? So I have the joint with x and y divided by the marginal of what we are given. So here's a nice introductory example. Suppose I have P of xy, it's a joint probability mass function of x and y, and let's say it's given specifically by these two values. So here you could see that x can take on the value 0, 1, and y can take on the value 0, 1. Let's calculate the conditional probability mass function of x given that y is equal to 1. Okay, so our first step is we'll find the denominator. So using this notion of a marginal with respect to y evaluated at 1. So I add the probabilities, letting x vary. X is 0 first and then 1. So this gives us 0.2 times 0.3. This would be 0.5. Now the conditional probability of 0 given y is 1 would look like this: P of 0, 1. Okay, so at P of 0, 1, we come up here, we grab it, 0.2 over the marginal evaluated at 1, which we figured out, 0.5. This simplifies to 2/5. And similarly, we get the conditional probability of x equals 1 given y is equal to 1. P of 1, 1, 0.3. We were given that, divided by the marginal of y evaluated at 1 is 5, so I get 3/5. So these conditional probability mass functions can take a little bit of extra thought. I will say this: I'll be looking at more examples of this in a video soon to be posted that I call Examples from Section 10. So that completes this overview video. I hope you've enjoyed it.